So Abhishek Dhar is a leading scientist in the field of statistical physics with international reputation. He's a successful alumni of our TIFR graduate school and receiving his thesis under Professor Deepak Dhar. He's also a part of our TIFR and leading the statistical physics group in ICTS. Among many distinctions, Abhishek received the ICTP Prize in 2008, Bhatnagar Prize in 2009, and he serves as an editor-in-chief in the Journal of Statistical Physics. So besides his excellent scientific achievements, what I personally found remarkable as a student and also now is that he's one of the very friendly, kind, and approachable scientists. And he has helped tremendously in strengthening the Indian statistical physics community, especially for students, by initiating the now famous ICTS Bengaluru Summer School and the Indian Statistical Physics Meeting. Abhishek has made profound contributions in heat transport problems, fluctuation theorems, aspects of quantum measurements, just to name a few. So his more recent interest is in the hydrodynamic theories for non-equilibrium systems. And he will give us a glimpse of his current work in this, on this topic in today's colloquium. So with that, I welcome Abhishek to start his colloquium.
Okay, so thanks, Trideep, for the very kind introduction and also for the invitation to both you and Rishi. Okay, so it's always nice to be back in TIFR, even if virtually. Okay, so today, so I'll basically, so there are two descriptions of matter. One is the microscopic and the other is the hydrodynamics. And the microscopic description is maybe Newton's equations or Schrodinger's equation, depending on whether you do classical or quantum mechanics. And then the macroscopic description is equilibrium statistical physics for equilibrium problem. And then there's hydrodynamics, which is basically the Euler and Navier-Stokes equations, okay, for a fluid. Okay, so basically I'll try to talk about the connections between these two pictures of that, these two parallel picture ways you can describe matter. Okay, so this work is done with so one of the postdocs at ICTS, Shubhadeep Chakraborty, and my student Santosh Kannappa. And they really know this work really well and would be able to answer all questions and all. And they did some really amazing numerics which was involved in this work. Then it was really good to have Paul Krapivsky, who joined us at a later stage. So in fact, he saw our paper on the archive and he made some very interesting observations, and we started doing some more things. So let me go to the outline of the talk. So I will describe this idea of these two descriptions of system, microscopic and macroscopic descriptions. And then I will talk about this blast wave problem, which is kind of an extreme example where one might be not sure whether the hydrodynamic description would work or not. Okay, so it's an extreme example to test the validity of the hydrodynamic description. Okay, so this blast wave problem, it's so the hydrodynamic description is basically looking at the Euler equation. So I will describe this in more details, but the rough idea is you have the Euler equations to describe how basically the basic fields that describe the system evolve in time. And there is a very famous solution due to Taylor, von Neumann, and Sedov independently of this Euler equations to describe this particular initial value problem where you have a blast and then ask how does it evolve. Okay, so I'll describe this solution. And then the idea is that you have some, and in fact, it's an exact solution of the Euler equations, which is quite non-trivial because it's a nonlinear problem, partial differential equations, and in spite of that, you have an exact solution. And so the main idea of our work is that you have this exact solution and you want to compare it with microscopic simulations. Okay, so for the same system, you just look at your atoms and how they evolve for some particular initial condition, And then you have predictions from hydrodynamics and predictions from microscopics, and you want to see how well they agree. Okay. So, so this is the idea. So it's a very extreme case where you might wonder whether hydrodynamics should apply, and we want to test how good is the agreement. Okay, so the main results are that we'll find actually there's a remarkably good agreement, overall agreement between hydrodynamics and Newton's equations. But then there are some deviations in the center of the blast. For this, we need to not just restrict ourselves to the Euler equations, but we have to look at dissipation and look at the full Navier-Stokes-Fourier equations. Okay, so I'll then describe these equations, and then I will discuss the main results. Okay, so please feel free to stop me at any time. Okay, so when we look at equilibrium physics, the basic idea is so there also we have the same picture. We have microscopic description where so let's consider this to be specific system of in one dimension where you have n particles with positions q1 to qn and momenta p1 to pn, and so this describes the phase point in two-dimensional phase space and completely describes the system. And then its evolution is described by a Hamiltonian, which has a kinetic energy part and a potential energy part. And let's assume you just have nearest neighbor or short range interactions. And then given the Hamiltonian, you can write Newton's equations, right? So velocity is equal to momentum by mass, and rate of change of momentum is force. Okay, so this is the microscopic description. And for equilibrium problems, we have a macroscopic description where we don't care about all the microscopic details of all the positions of the atoms and so on. But what we know is that it's enough to just say that, let's say if you are talking about gas in a room, that it's enough to say what is the total number of particles, what is the total volume of the box, and what is the total energy. Okay, and maybe the total momentum, which usually you work in the center of mass frame, so you can set that to 0. So if you know that these three numbers basically, that turns out to be sufficient to describe like the thermodynamic properties that you are interested in typically. Okay, and this is the idea of Boltzmann and Gibbs. So what they said is that you can compute this. So basically, if you have a constant energy, then in phase space that corresponds to some constant energy surface. And if you calculate the area of that surface, so let's I call that omega. So this is the area of that constant energy surface on which the system is the phase space trajectory of the system is confined, and you find its area. And then you define this entropy function S equal to K log omega. Okay, so clearly this entropy is a function of energy, volume, and number of particles. And from this, we can obtain all equilibrium properties of the system. For example, the equation of state, its specific heat compressibility, and all sorts of things. So it's quite an amazing thing that you can construct such a function which contains the complete equilibrium, all like whatever you can measure, it's all contained in this function. Okay, so this is the as far as equilibrium physics is concerned, and now let's go to non-equilibrium systems. Okay, so in this case, what we are interested in, let's say we are interested in gas flowing through a pipe, or water boiling in a beaker, or a cyclone, or let's say supernova explosion. Okay, so what is a useful way to describe such non-equilibrium systems? And here the idea is that one thinks of so this is the idea of local equilibrium. So if you have a big box which is kind of in not in equilibrium, you just divide it into small cells of some size, which are like you can imagine small boxes which still contain a large number of particles, and locally each of those small boxes is in equilibrium. And okay, so then what is the description? So let's imagine you have this channel which contains these molecules, and I divide it into these boxes of size L. Okay, so this L is still large enough to contain some large number of atoms. And to describe the equilibrium in such a box, I know that I need locally the number of atoms in this box, the total momentum of the particles in the box, and the total energy, right? So given this size L, these are the things I need. And then that describes the local state of the local equilibrium state of the system. Now, corresponding to this sort of macroscopic variables, I have sort of more intensive variables like density, velocity, and temperature, which I can also use to describe the local state of the system. Okay, so now the idea is that what is special about these three fields? It is that they correspond to conserved quantities. Okay, so the total number of particles is typically conserved, the total energy is conserved, and total momentum is conserved. And so these are the variables that are important in describing the system. Okay, and because they are conserved, they evolve slowly, and their evolution is given by the equations of hydrodynamics. Okay, so this is the idea of hydrodynamics. You just look at the conserved quantities, they form a field which will vary slowly in space and time, and they are given by nice simple equations.
Abhishek, okay. One question. What is the scale of this slowness or fastness? What's the scale?
Yeah, so this scale L is, it's a bit tricky to define, but right now I'll just, one way to think of it is like typically there's some maybe mean free path. If I'm thinking of a gas, then there's some mean free path, and it should be many times the mean free path. But a precise definition is a bit difficult, I think.
Okay, thank you.
Right. Okay. So yeah. So the main idea is that these fields evolve slowly, while all the other fast non-conserved degrees of freedom lead to effective dissipation and noise terms, as seen by the slow fields. Okay. So so there are these two. Fast degrees and slow degrees, and the fast degrees will see basically act like dissipative terms for the slow fields. Okay, so this we'll see in the hydrodynamic equations. Okay, so so again, how exactly do we go from the microscopic to the macroscopic picture? So again, just imagine I have this tube with gas molecules, and the microscopic description is the positions and moment of each particle, Qi, Pi, and these are of course functions of time. Right, and then the macroscopic description is these three fields: NXT, total momentum, and total energy. So how do I construct these fields given the microscopic fields, microscopic degrees of freedom? And so that's given in these three equations. Okay, so the density, which corresponds to the total number. So it's just a total number divided by the length of this small box. So the density is just given by this. So you just so this is mass density. So I put a factor mj for each particle, and then you just count the number of this delta function. Just counts the number of particles at the position x. Okay. And so similarly, I have a momentum field which just counts the total momentum at point x. And then I have an energy field which counts the total energy around the point x. Okay. Okay, so these are the basic fields: density, momentum, and energy. And from this, actually, one can also define a velocity field. So, so this is important that usually when one writes hydrodynamics, one defines a velocity field. So from the density and momentum fields, the velocity field is defined in this way. Okay, and okay, so okay, so now there's also one needs some connections with thermodynamics, and so for the energy field, one can write it in terms of the density field times energy per particle, and energy per particle has two parts. One is because the fluid is flowing, so there's a overall kind of center of mass energy, which you have to, which is just, so V is the flow velocity, so that's V squared by 2 is the kinetic energy associated with the flow. And then whatever is remaining is the internal energy of the particles. Okay, so so that's how this internal energy arrives, and this is something you have to use from thermodynamics. Okay, so the idea is that you assume each of these small boxes is in local equilibrium, and so you can use the laws of usual equilibrium thermodynamics to relate, for example, internal energy to the basic variables, which are density and temperature. And you can also write a pressure equation for which in terms of density and temperature. That's the equation of state, right? Okay, so
Abhishek, one question.
Yeah.
So when you are writing this epsilon is v square over 2 plus some internal energy,
yeah,
at some level there is a decoupling between what you would call the center of mass coordinate and whatever is happening within the relative coordinates of the box, right? Because v square by 2 is the flow velocity of the center of mass, roughly speaking, of the box that you are talking about.
Yeah, but at the locally.
Yeah, locally at the small
Right,
box.
Yeah. Right.
So how good does this, is it understood, like how good or where does this approximation remain, or where does this break down?
No, see, this is always, I mean, it's just like you are going in the center of mass, right? Like, for example, if I am sitting in a box and this box is moving at whatever speed, I don't care, right? I mean, finally, I can just remove all that energy, and then whatever remains is the internal energy. So, I mean,
but your internal energy does not depend on V. I mean, and in that sense, if you write it as a function of V, then of course it's a general statement. Yeah.
Right. Yeah. So I can always subtract of the center of mass energy. Right. Okay. So this is how you go from microscopic variables to the hydrodynamic fields. Okay, so now what I'll do is I'll just write the equations that are satisfied by the three fields. Okay. Yeah.
So these averages are done in the local thermal equilibrium, which are in the local field of local frame of this V.
This average is okay. So let's imagine. Okay, so this is bit again technical. I mean, so for each macro state, you will have some ensemble of micro states, right? And so you can imagine that this average you are taking over those all those micro states, which correspond to the same macro state.
Okay, but if you want to relate this quantities with rho and temperature, then you have to use equilibrium, thermal equilibrium state, statistical state, right?
Right. Yeah. So locally you have some. I mean, so see, locally you assume there's a local temperature, right?
Okay. So I'm saying this local thermal equilibrium is in the frame of V. That's what I'm asking.
Is in the frame of V. Yeah.
Okay.
Right. Okay. So yeah. So now let me just write. So tell you what the equations of motion for the hydrodynamic fields are. So I mean, so actually these equations of motion can be written down without actually caring about the microscopic description. Okay. So I mean, when Euler and all these people, Navier-Stokes and wrote these equations for a fluid, the hydrodynamic equations, they didn't care about how it came from microscopics. It's written purely phenomenologically. Okay, so so there are these three fields: rho, which is the density, the velocity field, which I am calling U, and the energy density, which I am calling epsilon. And so you have three fields, and there are three conservation laws. And this gives us the three hydrodynamic equations. Okay, so this is the first equation. If you look at it, it's a of particle number. So del rho del t plus so del rho del t plus divergence of the particle current, which is rho u equal to 0. And then the second equation, if rho u is the momentum, and this is like the momentum density. And this is the current density, rho epsilon. This is the energy density, and this is the energy current. Okay. Okay. So now these are the equations of hydrodynamics. So if there are the structure of these equations is okay. So there are some parts which I have marked by red, and these are known as the dissipative terms. Okay, and without these terms, if I set this to 0, then what the equations that I get are the Euler equations. Okay, so the Euler equations plus the dissipative terms, that's what is called the Navier-Stokes-Fourier equations. Okay, so normally if you have, when you write Navier-Stokes, people usually talk of just momentum and density, and you don't worry so much about temperature. So that's why usually people talk of are interested in Navier-Stokes and not Fourier. But in our system, we'll see that it's important to take temperature variations also. So you have to include all three fields, and then it's called Navier-Stokes-Fourier. Okay, so in the dissipative terms, you have something which is basically like what is the viscosity term, right? And in the last equation, you have something which is basically Fourier's heat conduction. Okay, so these arise from dissipation. Okay, so so I hope this nomenclature is completely clear. What I call Euler term equations and what I call Navier-Stokes equation. Okay, so
Abhishek, can I ask a question?
Yeah.
So the dissipative terms, I presume, are written in at the leading order of the derivative expansion. Is that right? I mean, in the sense that there could be the third derivative terms and so on, which will have other coefficients and so on. I mean, there is an understanding that this is the leading effect which are captured by just two constants, eta and kappa.
Yeah, right. Yeah. Yeah. So of course, there's this question of like, how do you derive these equations? And I mean, is this complete or do you have more terms? And in principle, I think, yeah, you'll have third derivative terms and so on. That's true. But yeah, so this is the minimal equations that one generally just writes down.
Right. Okay. Thank you.
And Abhishek, do you use some kind of fluctuation dissipation relation then between kappa and eta?
No. So right now at this level, I'm not even putting noise, right? So these are purely
right, but these terms are,
sorry.
But these terms are like some transport coefficients that you're putting by hand.
Yeah. So eta and kappa are the transport coefficients. One is viscosity and one is thermal conductivity. And in principle, you could compute them from like, so like given a microscopic Hamiltonian or a microscopic model, you can compute it using this Green-Kubo formulas, like linear response theory.
I see. Okay.
Yeah. So that, I mean, so in that sense, this, okay. So, right. Yeah. So let's look at the structure of these equations. There are three independent fields.
Sorry. Yeah. This Gautam's point also refers to a certain, you need to have a certain scale, with respect to which you can neglect higher derivative terms. What's that scale in your problem? Right.
Yeah, so this might be, I mean, so the only scale I can think of is this coarse graining length scale. Like if you have very low densities, it's possible that you can have this higher derivatives would become maybe more important. Or if you have very like shocks and all.
Yes.
So those are the, yeah, so those are actually questions like, I mean, how good is this, how good a description? If I just, so right now my question is, if I just look at this set of equations, which are the standard equations, then how does it compare? Now, if there is a problem, then one might imagine that it's actually, so then these are possible reasons which might fix the problem.
Yes, okay, thanks.
Yeah, I mean, sometimes people say that, the fractional change in various quantities in one thermal wavelength should be small. So that's one possibility which would work well at high temperatures. But you don't have any particular thing like that, for instance.
And Abhishek, aren't you using the fact that like the system the scale at which time scale at which system locally reach equilibrium, that is much faster than this time scale?
Yeah, so I'm assuming, of course, that there is local equilibrium, and there's other, I mean, so that is necessary for hydrodynamics to work.
No, I'm saying there's a time scale for the local equilibrium. If you just fluctuate a little bit, that reaches local equilibrium very fast, right?
Yeah, actually, that time scale over which the non-conserved quantities relax, I think that it's that time scale. So the time scale over which these fields evolve will be larger than the time scale over which the non-conserved quantities relax.
Yeah, exactly. Yeah.
Right. Yeah. So
one point just to maybe comment on Gautam is that thermal wavelength involves quantum mechanics in converting it to wavelength.
Yeah, that's what I was.
This is all classical. Yeah.
Right. Yeah. I was thinking about that. Yeah. So I mean, so the derivation of these equations has a lot of issues, which of course, is an open problem, I would say. Okay, but here the philosophy is that I just take these equations as the standard hydrodynamic equations, and I want to see, how well does it compare? And if it doesn't work, then I would ask all these questions. Okay, so
Abhishek, minor question. Is the temperature determined from the equation of state? Is there any way to think of it in a manner similar to the definitions you had in the previous page?
Yeah, right. Yeah. So, okay. So basically, originally I said that there are these three fields: rho, then momentum, and energy. I think I called it E. And now, now, for example, how do you? So in these equations, you see there's a in the second equation there's a pressure term. Okay. So what is it? This looks like new field. But here we have to use the equation of you have to use the fact that the system is in local equilibrium and pressure is given by the equation of state. So if it's an ideal gas, we would just write P equal to rho into temperature. Okay. And so what is temperature again? So I have this basic energy density, which is a completely microscopic quantity. And then I say that I can separate it into some center of mass part, and then some part which I call internal energy, and which I called U. And this internal energy, okay, so since I know E and V square, I know the internal energy. And from the internal energy, I know for a system in equilibrium, internal energy is related to density and temperature, right? So therefore, I know the temperature. So yes, I do use the fact that it's in local equilibrium. Does that answer the question?
Yes, thanks.
Right, yeah. Okay, so so the basic point is that there are three independent fields, and I can take them to be the most convenient and physical fields to consider are density, velocity, and temperature. Okay, this is what I would measure in a lab. Okay, so so I need some other information like pressure, which is the equation of state, and then the this relation for internal energy as a function of rho and t. These are things I know from equilibrium physics, right? Equilibrium statistical physics. So okay, so there's some information from equilibrium physics, and then the other information I need is this transport coefficients, which of course, when these equations were originally written, you just obtained them from experiments. But right now, what we know is that these equations can be obtained using linear response theory, starting from your Hamiltonian. Okay, so in that sense, there is a complete connection given a particular Hamiltonian system with these three conservation laws. I know exactly how to write this equation with all the with all parameters and everything. Okay, so so this equation basically tell me about how fluid flows through a tube, or about free expansion of a gas, and so on, and also about a supernova explosion. Okay, these are the simplest equations which describes a lot of phenomena. Okay, so I just want to say that the structure of these equations is that these have a form of just local conservation laws. So there's some charge Q del T plus divergence of the corresponding current is 0, right? And then this currents that I have, the three currents. These currents have two parts. One part is are called deterministic parts, and this gives rise to the Euler equations. So for example, for the momentum, the total current corresponding to momentum is rho u square plus p, and then minus eta del u by del x. Okay, so this is the total current. And this part is what I called deterministic Euler part, and this is the dissipative part of the total current. Okay, so so these are the reversible and Euler terms and irreversible dissipative parts. And other thing is that dissipation here basically refers to transfer of energy from the hydrodynamic fields to the internal degrees. Okay, so there's really finally it's a completely conservative system. Energy is not lost. So dissipation just means like when you stir, let's say, water in a cup, there's a flow, but eventually all this energy of the kinetic energy of the water, it goes into heating the fluid, right? So that's how the energy goes. So it goes into the internal microscopic degrees of freedom. Okay, so and then I already discussed the connection to microscopics of these equations. Okay, so now the main question is, how good is the hydrodynamic description? And so one sort of question is there a rigorous derivation of hydrodynamics from Newton's equation? And in fact, this is part of Hilbert's sixth problem, and so far it's unsolved. I mean, Hilbert stated it in a slightly different form. He said, can you derive hydrodynamics from kinetic theory? So he assumed kinetic theory, but of course, more basic would be from you to derive kinetic theory, you have to go back and from Newton's equation, how do you derive kinetic theory? So, but that was the basic idea, from microscopics to macroscopics. Okay. So this, of course, one is talking about a rigorous mathematical derivation. But from a physicist point of view, there's a lot of progress. I mean, if you start from just Boltzmann kinetic theory for the single particle distribution function, and there's a systematic way of doing some expansion in terms of a small parameter and deriving these equations. And I think in that expansion, you will get these higher derivative terms, if I remember right. Okay, and so is there a question? No. Okay, so recently, I mean, I just want to say that there's another approach that you can take is the idea of coarse training, which is the basic, basically what we do in want to do. We want to do this boxes of some size, and so then you have to project out the faster degrees of freedom. So there's a recent work where we have attempted this. So if you're interested, you can look at this paper. Okay, so now, so then the basic question is how accurate is the hydrodynamic description and what are the limits of its applicability? And surprisingly, there are very few precise numerical verification which look at the equivalence of the two descriptions. Okay, so and this is what we attempt here. So I just want to point out that there's a series of papers by R. Rajesh in math science and his students since 2019 or even earlier, where they actually started looking at this question, and they were looking at 2- and 3-dimensional blasts. And maybe I'll talk a bit later about their work. And so they did some really high quality numerical work. In fact, Rajesh gave a talk at ICTS, and I got interested in this problem at that time. Okay, so so we want to test how this limits of applicability of hydrodynamics, and in this context, we want to study a blast wave. So let me talk now about the blast wave, which is itself a very interesting problem. Okay, and it's basically a bomb blast, right? And you can imagine it's such an extreme event. I mean, you'll worry does hydrodynamics work or not. Okay, so the history of this problem is around the time of the atom bomb explosion in 1945. So basically, a bomb explosion is like you release a huge amount of energy in a very small region, and so this creates extremely high temperature region and with a sharp shock front. And one of the interesting questions is, I mean, how does it grow, right? I mean, how does the shock evolve with time? I mean, that's the most basic question you can ask, right? So how does the shock front evolve in time? That's one question. Okay, so now this question actually you can answer by doing some very simple dimensional analysis, and it's quite amazing. So this is something, I mean, I think students should just work out. I mean, it's quite amazing how powerful dimensional analysis is. Okay, so now imagine you have this bomb blast, and what are the so you just want to know how this the front is evolving. Okay, so let's RT be the position of the shock front at time t. So this is something of dimensions length. Now, what does this depend on? So this can depend on basically the total, certainly on the total energy that was released in this explosion, and it's expanding into some ambient atmosphere. So it depends on the density of that atmosphere, right? So let's call that rho infinity. So you have the explosion, and then outside you have some low temperature region with density of air is rho infinity, and the shock is going into that. Okay, so these are the only things you can that the R of t should depend on, and of course it depends on time. So then we just write simple dimensional guess that R depends on e to the power a rho to the power p and t to the power c, and you just do dimensional equate dimensions, and you get this this formula. Okay, so R of t depends on the energy times t square divided by some dimensionless constant a times rho infinity to the power 1 over d plus 2. Okay, so this is for a blast in d dimensions, and a is some constant. Okay, so now from this equation, what you can do is, let's say if you are in dimensions 3, then you find that the radius grows as t square to the power 1 by 5. So that's t to the power 2/5, right? So, and then there's some prefactor. Okay, and so when this explosion, during the atom bomb explosion, people collected this data of, so here, if you look at, this is the picture of the explosion, right? So this is at so this picture is 16 milliseconds after the detonation, and so this is already 200 meters high. And then you look at it after in a sequence of, you take a sequence of pictures, so you know exactly how this size is growing, right? So this is, I think, 0.38 milliseconds and 0.52 milliseconds and 0.66 milliseconds and so on. And okay, so you know how it's growing. So you can plot R as a function of time, and this is what was plotted from that explosion data. Okay, so here what is plotted is 5/2 log of R, and the x-axis is log of time. And as predicted by this formula, you see a perfect straight line. And because you know rho infinity, and you know actually this constant a, so you can determine how much energy was released in this blast. Okay, so in fact you get something like 10 to the power 14 joules, and which is in fact one of the best estimates for the energy released in that bomb explosion. Okay, so this is quite amazing that I'm just doing simple dimensional analysis. You can get such a accurate result. Okay, so sort of a maybe a more nicer example is the supernova explosion. So, for example, this is a picture of the Crab Nebula. I'm not sure if it is a real picture or maybe Rishi would know, or just a visualization. I think it's a real picture. But but I mean, this to understand this explosion, in fact, people use this. I mean, use exactly this analysis. Okay, and from this analysis, you can estimate how much energy was released in this explosion. Okay, and the estimate is in fact 10 to the power 43 joules. You can compare it with what was released in the atom bomb explosion. Okay, and from this also you can see, you can estimate how fast this the front of the supernova is growing, and you get some speed like this. So there's a nice discussion in this really beautiful book by Blanford and Thorne called Classical Physics. There's a chapter which discusses this solution of the Euler equations and this and its connection to the supernova. Okay, so now let me talk about, so right now we just looked at how the front is growing, but there are more interesting questions like what is the temperature profile inside the blast? Okay, what is the density profile? I mean, is it hottest at the center? Is it hottest at the sides? Those are obviously interesting questions. And what is the velocity field look like? So for this, we have to basically solve the Euler equations, right? So these are the basic equations, Euler equations, and now I confine myself to one dimensions, where you can do the same analysis. Okay, in 3 dimensions you can also do this same thing, which is what these people Taylor, von Neumann, and Sedov had done to analyze the atom bomb explosion. But we'll do the same analysis for the 1D case. Okay. So these are the equations. Again, these are the Euler equations. I don't have viscosity and I don't have heat conduction. And so those are somehow you can argue that those terms are not important when you look at, if you just want to see the evolution of this macroscopic fields. Okay, so so the first thing we know from the dimensional analysis that there's a shock front which grows in, so in 3 dimensions, it was t to the power 2/5, and 1 dimensions is t to the power 2/3. And this constant A, which is a dimensionless constant, it turns out that it can in fact be determined completely exactly. Okay. So now the idea is that we know that there's this growing front. So what Taylor and these people, they showed is that there's at long times, this set of equations has a very simple scaling solution. Okay, so so what they noted is that so you can define this scaling field Z which is dimensionless, scaling variable Z, which is the position X divided by the front position. Okay, so in terms of this field, what you find is that the density is given by this scaling form. So it's some some scaling function G of the scaling variable Z. The velocity field is given by x by t times some field which is again depends on just Z. So instead of depending separately on x and t, it just depends on x by t to the power 2/3. Right, and then just for dimensional considerations, you have to put this factor of x by t here and x square by t square here, right? And okay, so now and then there are some constants which are not important really. This just to make the subsequent algebra easier. Okay, so the main point is that you have the scaling form at long times. And now if you plug in these equations into this, plug in the scaling forms into these equations, then instead of this partial differential equations, you will have some simple ordinary differential equations for these 3 fields G, V, and Z. So these are some coupled ordinary differential equations, right? For this 3 fields G, V, and Z. Okay, so now to solve this problem, what you need also is some boundary conditions and initial conditions. So the boundary conditions, what you know is that there is a shock front, and at the shock front, what you have to do is basically you have to put in some, you have to say how you have to set some conditions for the discontinuity. Okay, and these are just like from the basic equations, you just integrate across the shock, and you get some sort of continuity equations. So these are called this Rankine-Hugonoit boundary conditions, and these are at the shock front. So you have 3 equations for the 3 fields. Okay, and then you have this conservation of energy, and so so you have a nice set of equations with some boundary conditions and some initial value problem, and it turns out that you can somehow solve this exactly and find this scaling functions G, V, and Z completely. Okay, so I won't of course go into the details. But so one trick is to define a new variable which is log of this Z. So Z is x by t to the power 2/3, and so that's a dimensionless variable. And then you make this transformation, and after that things kind of simplify, and you get some nice equations which you can solve. And so this explicit solution is given by these equations. Okay. So it looks a bit complicated, but it's an implicit equation. So the first equation, if you look at it, you can you have to numerically invert it, and you can find V. So V is the scaling field corresponding to velocity. So from the first equation, you know V as a function of Z, and then the second scaling field Z, which gives us the temperature, is given by this equation, and then this is the density, right? So we have the complete solution of the Euler equations. Okay, so this is what was given by TVNS for the 3D case, and we just adapted it to the 1D case. Okay, so this is just some remark that the shock problems and solutions of Euler equations and hydrodynamics. So some of the very standard references are these books by Landau, Lifshitz, and Sedov, and Zeldovich, and Reiser. Okay, so these are difficult to read, and it was really good to have Paul, who knew all these books, concretely. Okay, so that was quite useful. Okay, so now we want to come to the main question. Does the TVNS solution? So we now know this blast is evolving, and we have an exact prediction from hydrodynamics. Okay, hydrodynamics at the level of Euler equations, and we know exactly how the profiles are evolving. So now we want to do microscopics and ask how does it agree?
So Abhishek, so where is then the temperature is highest and inside the blast, and where is
I'll show that in a while.
Okay, sorry.
Yeah. So when I compare the microscopic, I'll show you the profiles.
Okay, thanks.
Yeah. Okay, so now let's. So I'll just come to some earlier work on microscopics. So one of the earliest work, I think, was this work by Antal, Paul Krapowski, and Sid Redner in 2008, where what they studied is, let's assume, so they studied this in 2 dimensions. So let's say you have a gas of hard spheres, a hard disk in a 2-dimensional plane, and initially at time t equal to 0, all of them are at rest. Okay, so you just randomly place these hard disks at rest on a plane. Okay, and then at time t equal to 0, you just hit one of them, and you ask what happens. Okay, so then this guy goes and hits some other guys, then it propagates, right? So this there's a front which evolves, and in this picture you can see that after some time, these are all the particles that are excited. Okay, so you can see that at the center there's somehow less density, at the edge there's more density, and so on. So in this early paper, what they studied mainly is they looked at how does the number of excited particles grow with time. And they found numerically they obtained this result, which actually agrees with what would be predicted from the TVNS solution. Okay, so this is one of the first studies, and then Rajesh et al. In 2010 they studied the same problem, but for a granular system where there's dissipation, which means that every time particles collide, there's some loss of energy. Okay, so for this system, what they found is this figure on the left. And there is quite interesting, so you start with the same initial condition, you excite one guy, and you find that, and you color the excited particles in these different colors. Okay, so, right, yeah, so, so these different colors basically tell you the excited particles at different times, and you can see it's very different from the elastic gas, which is shown on the right. So on the right is shown the elastic gas, which again Rajesh et al. They did for a much larger system than the one shown on the top, and there you find it just goes like in a spherical symmetric way. And there's some distribution and all that. Okay, so and they showed that this number of excited particles for the granular gas is very different from the elastic particles. Okay, so the scaling is very different. Okay, then more recently there has been more detailed comparisons with the exact the Taylor, von Neumann, Sedov equations and the microscopic dynamics. And what was found is that there is significant deviations between the hydrodynamics and microscopics. Okay, so this is what we wanted to, therefore, to explore in a more detailed way. and understand why there's a disagreement. So this is sort of obviously a very interesting question. And so what we thought of doing is to study actually even a simpler case, which is a one-dimensional gas. And this is what we look at. Okay, so the advantages of the 1D gas, unlike the 2D or 3D gas, is in 2 dimensions you have to work with hard disks or hard spheres, and there you don't know the exact equation of state, right? You have to do some virial expansion, so everything becomes much more complicated. In 1D you can work with point particles, and so you know the equation of state exactly, and also it's a system which thermalizes very easily, and simulations are much easier. So this is the advantages that we this 1D system is.
I have one question, Abhishek.
Yeah.
This von Neumann et al. Solution must be holding for a certain period of time only, no? After the detonation?
No, so this solution is good at long times, and it's good for all times, provided of course you don't hit some boundaries.
I'll tell you what is bothering me. What is bothering me is the mushroom cloud. Because what really happens when this detonation happens is that the vacuum is created inside and all the stuff from outside just is sucked up. That's what gives rise to the mushroom. So I was just wondering whether the problem changes.
Okay, right, yeah. So, okay, so so here of course I mean, so there are of course some big differences from with this setup and the actual setup. So the actual setup is actually a one-sided thing where you have I mean, so what was solved by TV, this Taylor and all, is a geometry where you have an explosion which is expanding. There's no, I mean, in a spherically symmetric geometry. Okay, but the real blast, of course, there's I mean, complete, it's sitting on the ground, and so we can see obviously it's going up, and so it's very different. So there, I think the only thing that you can expect to work is the scale, which is kind of very robust. And but then some details, because like you said, there's the mushroom, and which is because of it's highly asymmetric, right? It's not a spherical geometry, symmetric geometry.
No.
Also, I think the gravity is missing, right? So gravity
is also missing. Yeah. So I'm
give rise to this mushroom.
Gravity is important.
Yes,
right?
that's right. Yes.
Right. Yeah. So so I think so all those details can't be captured by this solution. But some things like this length scale at which it's expanding, I think that should be accurately reproduced, and which was indeed the case.
And how is it justified to use the hydrodynamic limit there? Because for hydrodynamics, you said that you need to use some local equilibrium assumptions, but in this blast, it's happening at a very fast time scale. Right? Is it?
Yeah. So that's exactly the question. I mean, why does it? I mean,
why does it work? Okay.
Yeah. So that's why I mean one would like to test it, right? I mean, because it looks like a limit where you might expect there should be problems. For example, there's a shock, right? At shock, there's like huge discontinuities and all. You might worry whether it will work.
Okay.
Sorry, maybe I missed this. So inside the shock, you assume the density and temperature, everything is constant.
No.
No.
No, inside there's a profile which is predicted by the by these equations.
Okay. So right. Okay.
Right. So the complete profile inside the shock is predicted by the TVNS solution.
Okay. And outside it is constant.
Outside it's completely constant, right? Yeah. So so inside you have some profile. Outside it's just ambient density is constant. Temperature is in fact assumed to be 0 because compared to this it's 0, and velocity is also 0. Right?
So did these numerical solutions compare the profile also? And that matches?
Yeah. So that is this work by Rajesh and collaborators, and also by this Trizak and collaborators. So this works actually compared in detail the complete profiles for the 3 fields with the microscopic simulations, and they found like significant deviations.
And in these inelastic spheres, you will assume that some of the energy is going into the internal energy of these particles. So the particles are getting some internal excitation. Is that?
So sorry, can you repeat again?
So the inelastic hard spheres. So that means that hard sphere is, for example, if some molecule then inelasticity means that some energy goes into exciting that internal degrees of freedom of the molecule.
Yeah. So some energy is lost to the internal degrees of freedom of
Right.
the
So it is
molecule.
not the dissipation that goes into Navier-Stokes.
No. Right. It should be very
It
clear.
is
It's not right. Yeah. So this is different from the dissipation I talk in Navier-Stokes. Right. So yeah.
Sir, here
Okay.
the number. What is the excited particle?
Which is the excited particle?
Yeah.
In this, okay. So you have initially everything is at rest, and you just excite one particle or two particles. Let's say it doesn't matter. So after some time, the initial condition is almost forgotten, and you will get this profile.
So like anything on the boundary is excited particle, or like is this? I don't understand.
No, so if you look at this, okay, so let me, so I just started. So if you look at this plot, initially you just excite one particle here. And so initially see everything is at rest, right? You excite one particle, then that excites a few other particles, that excites more particles. This is after a long time, you just plot all the particles that are excited.
Okay. Okay, thanks.
Right, yeah. Okay, any other questions?
So here, okay, maybe I can ask. So so what do you mean by exciting the particles? Is it giving it a momentum kick?
Yeah,
that will not be isotropic.
Right, yeah. So actually, maybe I'll show a video, then it will become clear.
But if you have a single particle we are exciting, then it will not be isotropic. You want to give a isotropic kick, right?
Right, yeah. So this is a video. If you give a single particle, for example, you'll find that the whole system has shifted slightly. Okay, so if it's a big system, you won't see, but initially you'll see that there's a slight shift of the whole thing. But you can give it isotropic, and then, okay, so in this case, I'll just show this video where initially everything is at rest, and you just excite 4 particles in some isotropic way, and you see how it evolves. Okay, so this is, I just plot all the particles that are getting excited. Okay, so this is some simulation that video that Shubhadeep has generated. Okay, so I hope this is clear. Okay, so now, like I said, because of this disagreements between hydrodynamics and microscopics, we want to study a simpler system, and this is the 1D gas, and this is our system. So you have a line, on the line you have particles which, so you have n particles with position, momentum and mass given by this. And you have some average density, which is total number of particles divided by the total length of the box, let's say. And okay, and here what we do is, you see these particles are colored red and blue. That's because you take their masses to be alternately different. Okay, so there one of them is heavy, light, and so on. So the reason is that if you take equal mass particles, then you can show that this system is an integrable system and it won't thermalize. But if you take the masses to be alternate, then it has very good ergodicity properties. It thermalizes very fast. Okay, so that's why we just take this model. But it's still point particles, which means that it has the same, it has an ideal gas equation of state, and which is very good, right? Okay, so okay, so the dynamics is basically this: every time two particles collide, they energy and momentum is conserved, so they reflect with different new velocities, v prime and vi prime and vi plus 1 prime. Okay, so this is just collisional dynamics. Particles move freely, and then they collide, and they emerge with some new velocities, and both energy and momentum are conserved, and this goes on. Right, and okay, so this is our microscopic dynamics, and then we want to take an initial condition which corresponds to this shock. So what we do is, initially all particle is at rest. Then in some central region, we give we choose particles and give them some give them some momentum and energy. Right, so we choose in fact their velocities from some Gaussian distribution, and to make sure that on an average there's no drift. Okay, so we start with some energy profile, and so this is what, for example, if you plot the okay, so here what I show is at time. So this is time, and this is position space, and so at time t equal to 0, all the particles are at rest, And then in this small region between, let's say, -5 to +5, all the particles that are there are given some energy and momentum, right? And then they excite more particles, and I plot the space-time trajectories of each of these excited particles. Okay, and this is how you will see that this system evolves. And this dashed line that I have drawn here is in fact is this function R of t that I talked about, the shock front. So you can see that from the microscopics, the shock front predicted by hydrodynamics is actually pretty good. There are some small fluctuations, but it more or less follows the shock front that is predicted from hydrodynamics. Okay, so now this is a
so Abhishek, this boundary is t to the power 2/3 or something. Is that right?
Yeah, t to the power 2/3, right?
Okay.
Right. Yeah. So okay. So this is a single realization of the system. And now what I'll show is what you can do is you can start from initial conditions, a large number of initial conditions, where you always excite only particles in this region at a given temperature. Okay. And so you do some sort of averaging and compute these three fields, rho, velocity, and temperature. Okay, so these are the three fields that we compute from the microscopics, and this average, like I said, denotes an average over initial states. Okay, initial microscopic states. Okay, so now if I so this is from the microscopics, what I find is that if I plot space-time evolution plots of these three fields, this is what they look like. So this is density. So what you can see is that the density at the center is very low, and the density at the edge is kind of high. Okay, and velocity similarly at the center is very low velocity, and at the edge is high. And the temperature actually at the center is again is reasonably high, and there's some profile in the temperature. Okay, so now so this is space-time plots, but let's just look at snapshots at a given time. What does rho of x look like? What does v of x look like? And temperature look like? Okay, so these are the plots. So on the left hand side, I have plotted rho of xt, v of xt, t of xt. So this is what Srideep wanted to see. So density, you can see it's so the average density outside is 1.5 in some units, and you can see that the center is kind of low density, and then it grows in some way, and then there's a shock front, right? Then suddenly there's a drop, and it's the ambient density outside. Okay, so this is the profile for density. For the velocity, again, you have some profile like this. At the center, it's because it has to be symmetric, right? Both ways. So at the center, there's zero velocity, and then there's some profile, and then it should drop sharply. And temperature, it's really hot at the center, and then there's some profile. Okay, so these are at profiles at different times, and then what we want to see is we have a scaling solution, which means you have to scale the data, divide x by t to the power 2/3, and multiply rho by some factor, and then see if the data collapses, right? And the collapse function, there is an exact prediction from TVNS for the three collapsed scaling functions. Okay, so on the right hand side, that's what I do. I do the scaling. I do the scaling according to the predictions of the Euler equations, and you can see that you get quite good agreement, though not okay. So there are some differences, but let's say if you look at the first plot, it's quite good. And sorry. So I mean, I'm kind of overshot time. So I mean, how much? When should I really stop, Rishi?
Yeah, maybe you can take 5-10 minutes more.
Then okay, I'll try to. Yeah, I'll definitely do it within 10 minutes. I think I should do it. Okay, so so it's 7. Okay, I'll try to stop in 17. Okay, so you can see that you get a good collapse, and so if you blow up this region, you can see that at larger times actually. So the dashed line is the TVNS prediction, is the exact solution that I talked about earlier, and you can see that the simulation results are getting closer to the exact solution at larger times. Okay, so if you look at larger times, it's getting better. both at the edges and at the center. Okay, so these are the places where you would worry things might go wrong because there's shock, and this place is really hot, so there might be some problem. And these are the, but you see that things are getting maybe a bit better. But if you look at the temperature here, you see that at the shock, things are getting definitely better with at larger times. So remember that the scaling solution is supposed to work even better and better at larger times. And this is true at the shock front. But at the center, there is a serious problem. The TVNS solution, in fact, predicts the divergence of the temperature field at the origin. And we know that in a physical system that cannot be, right? And in the simulation, you find that it is kind of bounded. Okay, so so this is what we find. Overall, pretty good.
Can I ask a question, please?
Yeah.
Abhishek, isn't this temperature plot a little bit counterintuitive? I mean, or you have some intuition which explains this?
I guess at the center, I mean, I would expect it. Yeah, sorry.
Yeah, please go ahead.
At the center, I would guess that it should be hot. I mean, so are you talking about the temperature profile or?
No, the temperature profile.
Yeah, so temperature, I mean, I can, okay, so initially, let's say you have some uniform temperature, but because this energy transfer is happening from the internal degrees to the velocity field, I think at the center, this transfer is less efficient in some sense. So that's why the temperature kind of, yeah, but I think I don't have a complete, like, I don't really have a deep understanding, I think, physical understanding.
Abhishek, this divergence at the center, is it related to the fact that the density is going to 0 at the center?
No, those, I think they're independent facts. I mean, the density does go to 0, and but I don't think they're, I don't think they're related.
I think this is a temperature per particle, and the number of particles at 0 is going to 0. Okay.
Yeah, there is a problem here. I mean, there is nothing there actually. Density is going to 0.
Density is going to 0, right? Yeah.
Then how come the temperature is shooting up this way?
Right. Yeah, but this is from the right. So
I think in the left plot it is clear there.
Sorry.
So if you see the left plot, the temperature in the center is also going down with time.
No, the from the simulation you can see it's going up.
No, if you see the left plot, this is the scaled version, right?
Right. Yeah.
The actual temperature is actually going down.
Yeah. So the physical temperature going down, but I'm saying from the TVNS solution, if you look at the actual temperature, not the scaled, even the actual temperature actually diverges. But the physical temperature, of course, doesn't diverge, and so so that is what we want to understand now. I mean, so what is wrong with this TVNS solution, right? So that is the main question now. I mean, why does it predict temperature divergence? Okay, so the main observations are that there's a very good agreement between simulations and Euler prediction, except in the blast core. And so then we asked, is dissipation important? Okay, so this is, so we dropped when we wrote the Euler equations, we dropped this dissipation terms. And this is now the question that maybe we shouldn't have dropped these terms. Okay, so now how do we see if these terms are important? So what we can do is we can take, for example, the ratio of this term with one of these terms, and just from some simple dimensional arguments, using the TVNS solution, look at this ratio. Okay, so ratio of the dissipation to the Euler terms. Okay, and is this small or not? Okay, so we neglected these terms. Now, where we justified in neglecting these terms? Okay, so now if you look at this ratio, then it turns out that near the core, near the core, it's actually has okay. So this is some calculation which I won't go. But finally, what you find is that This is given by depends on time and position in this way. And so you can see that at x equal at small x, or more precisely in a region of this scale, this quantity becomes large, right? So there is a small core region where it's not right to ignore this dissipation. Okay, so there's conversion of energy from this flow to the microscopic degrees, which cannot be neglected, and so we have to deal with the full Navier-Stokes equation, not just the Euler equations. So this is the problem. Okay, so I hope this point is clear. So so outside this region, it's okay to drop these terms, and that's why we see a good agreement. But inside this region, we have a different scaling solution. Okay, so now once you look at the full equation, so like I said, for the Euler equations, you have an exact solution. But once you take the full Navier-Stokes equation, there's no exact solution. And then what we did is just numerical simulations and of this full hydrodynamic equations. And so then what you find, so now I'm just comparing the full numerical solution of the Navier-Stokes-Fourier equations with the microscopic, with the TVNS solution. Okay, so now what you find is that this, once you do this, you find that this divergence is avoided. So the temperature is of course finite, right? So this divergence of the Euler equation is indeed avoided. Okay, so let me now finally just compare these three results: direct microscopic simulations, Euler, and Navier-Stokes. Okay, so so let's just look at the temperature profile. So the dashed line is the Euler equation. Yeah.
So in the previous slide, the solutions of this Navier-Stokes equations and the microscopic, how do they compare? Did you?
Yeah. So this plot has all three.
Okay.
Right. So here I plot TVNS is Euler equations. That is an exact solution. That's the dashed line. NSF is Navier-Stokes-Fourier numerical solution. That is this blue line. And then microscopic is this red line. Okay. So the main point is that, okay, so except in the core region, of course, we have good agreement between all three. And in the core region, the NSF is doing better than the Euler equations. But there is, of course, we still don't have perfect agreement, and that's still an open question. Okay, so basically now the idea is that we have in the core region, there's a different scaling solution. And so there, in fact, we can figure out, so there we have to write the full equations and ignore some terms in the Euler equations, and then you can again ask what is the scaling form, and this is the particular scaling form that we get. And these funny numbers that we get, 55 by 93, 50 by 93, and so on. So this depends on the choice. So in our dissipation, we have this viscosity and thermal conductivity. And the thermal conductivity, of course, depends on the thermodynamic parameters like density and temperature. And this dependence is, there is some rho to the power 1/3 and temperature to the power half and so on. And that eventually leads to all these funny powers. Okay. So, so what we found is that indeed we verified that the microscopic solution satisfies these scaling forms, but the scaling functions that we don't get complete agreement. Okay, so the last slide that I have that I want to talk of is, okay, so right now what I talked about is that you do an average over initial conditions, okay. But the other thing that really, I mean, especially mathematicians would be interested in is looking at empirical densities, which means you just look at one snapshot of the system, right? When we do an experiment, we don't do an average over initial conditions. We just look at one snapshot. So that's an empirical density. Okay. So we also looked at this empirical density, which you have to do with larger number of particles and some way of efficiently doing coarse graining and so on. And what we found is that this empirical densities also, follow the same equations as, they have the same behavior and they in fact follow exactly the same profiles as the averaged profiles. Okay, so this is a very nice thing that I think we could see. Okay, so let me just conclude. So what I discussed is there are two descriptions of the air in a room: an atomistic description and the continuum.
No. Last finish.
Due to Euler, Navier-Stokes, and Fourier. And the question was, is this description always valid? And we tested this in the problem of evolution of a blast wave. In particular, we consider a one-dimensional ideal gas, and for which there's an exact solution of the Euler equations due to TVNS. And we simulated a particular system which has very good, whose equation of state is known exactly and has good thermalizing properties. And we find really remarkable agreement between simulations and predictions from Euler, unlike the earlier studies that have been done in 2 and 3 dimensions. And we find some deviations in the blast core, which we understand partly as arising due to dissipative terms, which we need to include. And we don't have a complete, so there are these 2 scaling solutions in the core and in the outside the core. And to obtain a complete solution, you have to do some asymptotic matching analysis, which we still haven't done. But then the main difficulty in getting complete agreement in our particular system is that these transport coefficients are in fact not known so well in terms of the thermodynamic parameters. Okay, so this is the main difficulty. And in fact, this is of course the other problem of anomalous transport in low dimensions. The thermal conductivity, in fact, is supposed to diverge in low dimensions. Okay, so in spite of that, the fact that we get this very good agreement, that's quite amazing. Okay, so these are the references, and this is the other paper I referred to where we try to do a microscopic derivation of hydrodynamics. So sorry for overshooting a bit, but thanks.
Okay, thanks, Abhishek. I think we already had many questions, but we can have a few more.
Hello, Chandan here. Can I ask a question?
Yeah.
So this is related to what you showed in your last slide, where the instantaneous fields, they of course show fluctuations.
Right, yeah.
So my question was, people also write down equations of fluctuating hydrodynamics, where in addition to the terms that you already have, there is also a noise, and this noise satisfies some kind of a fluctuation dissipation theorem. And so the question is, these kind of fluctuations can be captured from the equations of fluctuating hydrodynamics.
Okay, so so far, okay, so fluctuating hydrodynamics, so far people have used to study fluctuations in an equilibrium setup. But here, of course, it's a non-equilibrium evolution, and on top of that, there are fluctuations. And for that, I think even the equations are, people are not sure what the correct equations are. So only for the equilibrium case, this is this work of Spohn and all. There one knows how to write these equations, but in the non-equilibrium setup, actually, it's it's not really known how to write these equations.
Yeah, it is not known rigorously, but people have written down equations that they assume or they expect will be valid, where you have a noise term, and that will give you some fluctuations. But if these fluctuations actually agree with what you're seeing in your numerical work, that remains to be seen.
Okay, right, yeah, that one can check. Right, yeah.
Can I ask a question here, Chandan? What are these fluctuations in which parameter, in temperature or what? So all of these things, for example, if you look at the velocity, temperature,
they
vary in space, and also they will vary in time, because this is one snapshot. If you take another snapshot, then you'll get different values. Yes. No, so these are the fluctuations. I was just asking about fluctuating hydrodynamics. You'll put some noise term. What would be the coefficient there? What is the scale of the fluctuation? In the equation for the momentum density, you can put in a noise, and since the total momentum is conserved, this noise also has to be a conserved noise. Yes.
And its correlations will be related to the viscosity. This is the fluctuation dissipation theorem.
Okay.
The transport and noise, their statistics are related to each other.
Yes. Okay, good. Thanks.
Yeah, Abhishek, just one question. So what's the bin size, I mean, that you took in these graphs? I mean, does it matter what kind of bin size?
So that's that's an important point. So here, see, one thing which we first did is just okay. So you can, I mean, you can put bins like that. Okay, and then if you make two big bins, then it's not nice. And if you make two small bins, it's not nice. Then what we did is actually we put kind of sliding bins.
Oh, I see. So the bin size is different in different regions.
No, it's the same size, but we slide it, right? I mean, so I mean, this is a bin, and then which is centered at this point. And then I mean, then you take a bin which is just shifted by a small amount. It is same size, but then you get a point somewhere here.
I see.
Right, so these are called sliding bins, and this gives you a smooth, and also you don't you can take reasonably large sizes. I mean, here I think each thing had like maybe 50 particles each bin.
I see. Okay, I'll ask you later about this thing, because I had some trouble, fixing bin sizes in some things earlier. Yeah, I'll ask you. Thanks a lot.
Can I ask a question?
Yeah.
Abhishek?
Yeah. Hi.
Can I ask?
Yeah.
Is viscosity important in this? See, because heat conduction, when TVNS drops heat conduction, that is because they take the limit of the scaling limit first, and then they solve the equation. But the thing is that heat conduction adds a boundary condition, which is, what's the word for that? Which is different from the limits are important. Whether you take the scaling limit first and then solve, or solve and take the scaling limit. But viscosity does not introduce any of the boundary conditions in the problem. So is viscosity important for the matching with the TVNS?
So you're talking about boundary conditions at the shock front, is it?
No, the heat conduction term, if I keep in the Navier-Stokes and try to solve for the blast, then you have to put the del T by del X is 0 at the shock center at X equal to 0, which if you drop the heat conduction term, that boundary condition is not there. So that makes a difference in the solution. If you solve with this boundary condition and without this boundary condition. Now, the viscosity does not involve any such term. So if I drop the viscosity and were to compare, does it compare well?
Okay, so in our case, so I think in this case, if you drop, somehow the viscosity didn't play much of a role. If you drop viscosity completely, also it gives the same thing, but the agreement, we don't get a better agreement.
Yeah, no,
it reproduces qualitatively the same features as you have with viscosity. So
so the other question is, if I choose this heat conduction term, is it sensitive to the value of kappa I put in? Like we are putting kappa root T as the heat conduction term.
Yeah, and we also put some rho to the power 1/3.
Yeah, but is the constant in the front? Does it play any role?
This constant.
Yeah.
No, see, this we actually tried with lots of different things. We changed the powers, we changed the coefficients, and this. I mean, see, finally, if you want exact agreement, you have to know what is it exactly, right? But qualitatively, we don't find any big differences if you change all these things.
So the point is that it does introduce a new boundary condition, heat conduction. Probably the value of, even if I make instead of root T, if I make something else, probably it won't matter.
Okay, but the root T is kind of almost rigorous.
No, I know, but I'm saying
okay.
the role of reconduction is only to make this boundary condition different to the Stokes center.
Okay, so apart from boundary condition, I would also look at this ratio.
Yeah. Okay.
I don't know if it's the same thing.
Yeah, so for very small x, heat conduction comes into role play, I guess.
Right. Yeah.
Okay. So when we were trying this in 2 dimension, and actually the smallest heat conduction you put in changes the answer quite drastically. That's why I understood.
Oh, is it? Okay.
Okay.
Right. Yeah, this we can discuss maybe later.
Yeah.
Abhishek, I had one question about your this related to Rajesh's question about determining this kappa and things exactly. So for your model, you had the model in 1 dimension where the particle masses are alternating, right?
Yeah.
But in the case where all particle masses are the same, that problem is exactly solvable, which you and Sanjeev did for this tracer particle, where you can write down the end particle. Now, for the case of this interchanging particle systems, can you write down similar kind of mini particle solutions?
For the equal mass case.
So for the equal mass case, you can write it down.
Yeah.
Right? Because you can just exchange. Yeah. Because that's what you did for the case
you're
of
talking about tag particle position and so on.
No, so while doing the tag particle position problem, I guess you can write down probably the end particle evolution when all particle masses are same. By using the fact that these are point particles, so when they just crosses trajectories.
Right, yeah.
So when I'm just thinking that, is it possible to generalize that approach for alternate systems?
Oh, no, you can't do anything.
No.
That's a very special integrable point, right?
Yeah.
The minute you make the masses different, all those methods go out of the window, right?
Right, yeah. You can't do anything.
Yeah.
But although the alternating masses is making your system more equilibrate locally rather than...
Yeah, but it's not integrable anymore.
Right, I see, yes.
It doesn't have infinitely many conserved quantities.
Right. I see, okay,
Right,
yes.
yeah.
So okay. I see.
Abhishek, you must have calculated the thermal conductivity of this system earlier when you are looking at
yeah, so
conductivity of
so that is the
systems.
Yeah, so that is the funny thing. So the thermal conductivity is supposed to diverge, right?
Ah, okay.
So I mean, yeah. So this is of course a puzzle. I mean, so okay. So when people write this hydrodynamic equations, even let's say fluctuating hydrodynamics or whatever, so there the idea is that when you write these equations, what you're thinking of is like a bare thermal conductivity which is finite, and then what you measure in this the heat conduction experiments, that is kind of a sort of renormalized thing which diverges. Okay, so the idea is that in the hydrodynamic equations, it's some bare transport coefficients.
But in your work, you know the scale dependence of how it diverges also, right?
Yeah.
From your earlier. So
right.
If I use the scale corresponding, so I guess there is some, you can make some claim that it is of that order, right?
Right, yeah. So I don't know if
you know how it diverges with L, right, from your earlier work.
Yeah. But here, of course, we are looking at an infinite system, and the L might be this coarse graining region and something like that.
Yeah, that's what I was saying. So if you can set up something like that.
Yeah, that is possible. Yeah, that is right. Yeah, that's a possibility. That
also, is it not possible to get those from fluctuation dissipation relation, which sometimes in fluctuating hydrodynamics gives you a relation in terms of this double derivative of local free energies? So, in the case of just diffusive systems, when you try to do fluctuating hydrodynamics, the mobility and the diffusivity ratio, you can write in terms of this double derivative of free energies, which is the fluctuation.
Yeah. But for I think 3 fields, you don't have such.
You don't have, okay.
You don't have any such results.
I see, okay.
So Abhishek, don't you think that this thermal conductivity diverges at a length scale, as Kedar was saying, that is, I mean, if you look at system sizes, so after some length scale, you will see the divergence. But if your length scale is less than that length scale, then it probably will have a finite thermal conductivity.
No, but where do we put the length scale? I mean, so the only thing I can imagine is in the coarse graining.
Yeah, so I'm saying that the coarse graining length scale, if that the length scale is smaller than some length scale, I'm saying because actually I actually studied one similar problem in the same system, but the dynamics is a bit different. And then there I measured this thermal conductivity, and you see that the thermal conductivity shows a diffusive scaling at smaller length scale, and it crosses over to anomalous scaling. And there is a length crossover length scale. So I was thinking that if your coarse graining length scale is actually less than the crossover length scale, then probably you'll see a finite thermal conductivity.
Right. Yeah. Okay. Yeah. I'm not sure. Yeah, we have to discuss this later.
I think there is some ambiguity as to the definition of what you call the bare thermal conductivity. I mean, what you're measuring in simulations is no longer the bare one. I mean, it of course depends on length scale.
Right. Yeah.
But what is the? I mean, as you said, in hydrodynamic equations, one would want to put in the bare transport coefficients, or is that?
Yeah. So in the hydrodynamic equations, when like for example, in fluctuating hydrodynamics, when we write the dissipative terms, what so we have this bare transport coefficients, and then of course finally the prediction is that the thermal conductivity diverges. Right? But so you're asking what are these bare?
So what is the bare thermal conductivity? That, I mean, how do you determine that?
Right. Yeah. So if you, for
that's
example,
what I guess. Is there a well-defined coarse graining scale in this problem? I guess that's equivalent question.
No. So I mean, so this is exactly what we attempted in this paper with KG Saito and all that I referred to. I mean, is there like, so the usual Green-Kubo formula will give a divergence, but what we say is that there is some coarse graining procedure which gives a finite number. So there's a modified Green-Kubo formula with some specified coarse graining. Yeah, I mean, I don't have a very good physical understanding.
Okay, let me interrupt a minute. So I think the discussion can go on. So the Zoom meeting will keep on running. But let's thank Abhishek for a wonderful colloquium, and I will stop the recording here now.
Yeah, thanks.
Yeah, thanks, Abhishek.